Okay, folks, good morning. This is the session on RPKI. If you're not in the right place, you should probably go somewhere else. So with that, hopefully we have everyone here who will be here after the session change. So we'll go ahead and get started. Our first presentation is the Cure to Vulnerabilities in RPKI Validation, which would be exciting. And we have Nicholas Vogel from Goethe University, Frankfurt, giving the talk. So take it away.
Thank you. Hello, everyone. My name is Nicholas, as was already mentioned, and I will be talking about vulnerabilities in the RPKI validation. And let's kick things off with a very short introduction to RPKI. So, as hopefully some of you are aware, RPKI is a cryptographic security extension to BGP, the Border Gateway Protocol, so the interdomain routing protocol of the internet. And with the RPKI, routers can get information on who is authorized to send certain BGP messages, announcements, and therefore filter and protect against hijacks. And RPKI achieves this by having a set of distributed repositories around the internet, basically servers that contain files, and systems uploading authorization objects to these repositories that contain information about who is authorized to announce their prefixes over BGP. And so then systems can use this RPKI information to make the routing decisions. And between the routers and the repositories, you have a software component, which is called the Relying Party Client, the RP. And this is the software that implements all the client-side RPKI functionality. So the routers don't have to implement RPKI themselves. They just interact with the RP, get all the RPKI data, and then can make the routing decisions. So let's take a deeper look into these relying party clients, into this software component. So RPs are, as I said, installed in a system to enable basically using RPKI information. And the RPs interact with the RPKI by first going to a set of hard-coded root repositories and downloading all the RPKI objects in these repositories. They then parse these objects and then check the fields within the objects for their validity. So for example, they check if the field that states the location of the object is actually the location on the server. And they also check, for example, if the issuer stated in the object is the issuer that really issued the object. And then in the next step, the RP will check if the signatures on the objects are valid. So all objects in the RPKI are signed. So the relying party needs to check for each of these objects if the signature is valid. And then after the objects have been validated, the RP has two options. Either it found URIs to new repositories within the repository, then it will go to these new repositories, download all the objects from there, and then continue the cycle, again parse them, check the fields and so on, and then again check if it found new repositories. And this continues in the circle until all repositories have been found, at which point the RP will finish the circle and then compile all the RPKI information into a single file, which is called the VRPS file, and then make this information available to the routers. And it's important to note that the relying party, which is installed in the system, is a trusted component by the system, which means that the routers do not implement any validation of signatures themselves. They just rely on the relying party to do all the heavy lifting, all the signature validations, and provide the information basically in plain text to them to make routing decisions. And the second thing to note is that the RPs need to be available because the routers don't have their own functionality to interact with the RPKI. So if the RP is not available, then the routers don't have any means to communicate with the RPKI, and so the protection will effectively be downgraded, and the routers will be vulnerable again to routing attacks. And this motivated us to take a deeper look into the security of the RP software implementations. And for us, the obvious solution was to use fuzzing to check these components. And we tried to fuzz the available implementations of relying parties with existing fuzzers, and we quickly noticed that fuzzing RPs is very hard. And this has multiple reasons. So first of all, generally, of course, fuzzers mutate objects to find vulnerabilities. So they have either start from scratch or have a corpus and mutate these objects to find deeper parts of the code and then hopefully trigger vulnerabilities. But for RPKI, this is difficult because all the RPKI objects are signed. And the fuzzers have a very hard time, of course, to create valid signatures, because if you just mutate the objects, as soon as you change a single bit in the object, the signature will be invalid, and so the processing will fail in the first step and not even reach deeper parts of the code. Then secondly, even more importantly maybe, RPKI validation does not only include single objects. The RPKI validation pipeline is quite complex. It includes multiple objects with multiple signature validations and field comparisons and hashes and so on. So if you want to test a single object, you can't just feed the single object to the RP. You need multiple other objects and fields until your object is even looked at, even parsed. And this is very difficult to achieve with normal fuzzers. And then the last thing is that fuzzers usually work with raw data. And the RPKI objects are very complex. They have a lot of fields. They have a very delicate structure. So you will have a hard time with a normal fuzzer to reconstruct these objects, and therefore generally parsing will fail and you won't reach any deeper parts of the code of the software. So we concluded after some frustration that using traditional fuzzers will be hard on RPKI software, and we need something else. Which is why we developed our own solution for fuzzing RPs, which we called Cure. And the basic idea of Cure is to combine the functionality of a fuzzer with the functionality of traditional RPKI software. So Cure implements all fuzzer functionality that you need. It can generate and mutate objects. It can feed these objects to the software. It can look if the software crashes, and it can even find inconsistencies like differential fuzzing between different implementations. And additionally, Cure also implements RPKI functionality. So it's capable of signing objects. It's capable of changing fields, constructing valid RPKI repositories, and thereby achieving a completely valid-looking RPKI state, like a repository, while still being able to fuzz. And in the design of Cure, the speed was very important, right? Because a fuzzer needs to be as fast as possible to test as many objects as possible and hopefully find a lot of vulnerabilities. And so we created Cure to be as fast as possible, and we decided to not use an existing implementation of an RPKI repository, but build our own, which is optimized in the right places to generate enough objects for the fuzzing. And in fact, in the end of our project, Cure was faster than all available RP software could even process the objects. So we could generate objects faster than the RPs could process them. So the setup was limited by the RPs and not by our implementation. And let's quickly go over the inner workings of how Cure works. So we have basically 3 different parts of Cure. And the first part is the object generation. So we need to generate manipulated RPKI objects in some form. I will go in the next slide in a bit more detail how it works. But then this manipulated object is fed into the Cure software, which first sets necessary fields and signs the object, if that's possible, if the object is possible. Then it will, what we call, repositorify the object, which means the object will be nested in a completely valid RPKI repository. And this is a very flexible implementation, so you can put in any RPKI object types, from which I think 11 exist. I might be wrong. And you can plug it in and repositorify any object. And then Cure will, in the end, make this repository available to the RP implementations over an RPKI communication protocol. And so you can plug in any RP that you want. So the implementation is completely independent of which RP implementation you want to look at. It just implements a standardized interface. And this also allows us to test multiple RPs at once. So we basically run Cure, create a repository, and then execute multiple RPs, and then check for crashes and also check for inconsistencies in the validation output. Now let's quickly go over our object generation. So we implement 2 different modes. The first mode is random byte mutation. So we just put in a valid RPKI object and then flip random bytes, switch random bytes, and so on, which will generally not result in a valid object, but it will be able to trigger potential bugs in the parsing of the RPs. And the second object generation we implemented is structure-aware generation. And in this generation mode, it will generate valid structured RPKI objects which have some manipulated fields, but generally the RPs should be able to parse these objects, and therefore we should be able to reach deeper parts of the code. Okay, let's come to our results. So with Cure, we were able to find 18 severe vulnerabilities in the in different RP implementations. An overview is given below, and 5 CVEs have been assigned, and we also found additionally 7 RFC inconsistencies, so cases in which different implementations reacted differently to the inputs and came to different validation results. And I will now go through the most severe vulnerabilities, and I will start with the most severe one we found, which was a path traversal attack. And to understand this, you have to know that the RPs generally use the object names as storage locations on disk. And you can maybe even already see where this is heading, because if you just put in a path traversal in the object name and it's not properly escaped, it wasn't in one RP, then you can achieve a path traversal and thereby place arbitrary files anywhere on disk on the server running the relying party. And I guess I don't have to explain why this is a problem. But we also found one interesting application of this vulnerability, which is a cache poisoning attack that exploits that on the RP server there's one specific folder that keeps the trust anchors, so basically the inherently trusted keys. And the attacker can use the path traversal to place his or her own key in this folder and thereby achieve a complete cache poisoning of the RPKI software, of the RP, because the attacker can just get arbitrary objects validated because the attacker has a root trusted key. And we also measured how many RPs are affected by this vulnerability, even after we disclosed it and it was patched. And we saw that in December, over half of the RPs on the internet were still vulnerable to this attack because they haven't patched yet. So if you might be running an RP, I really want to strongly motivate you to maybe update your software. Then the largest amount of vulnerabilities we found were denial of service vulnerabilities. So vulnerabilities that allow an attacker to crash an RP implementation and thereby downgrade RPKI protection in any system. And we found crashes in multiple modules of the RP, so for example, in the parsing, but also in deeper processing, and even in the processing of RTR requests, which is the module that interacts with the routers. And the problem is that the impact is quite big because any attacker can attack all running RP instances in the internet by just setting up an RPKI repository. Because as I said in the beginning, all the RPs query all RPKI repositories on the internet. So if you set up a repository, then all RPs on the internet will come to your repository and download and parse your objects. So by just placing a malicious object in your repository, you can effectively crash all running RPs of a given software implementation. And up to this date, on December, when we measured this, still over half of the RPs were vulnerable to a denial of service because they haven't patched yet. Then one more thing we found was that we found processing inconsistencies in different RP implementations. These mostly stem from vaguenesses in the RFCs, which, for example, specify a certain check, but don't specify certain edge cases, and then different RP implementations implement these checks differently, and therefore come to different results on if a certain object is valid or not. And we will later see why this is a problem. I will first now also talk about cache disparities that we found, which is not really that exploitable yet, but it might be a problem in the future where different implementations will not process a certain repository if objects are too big. And first of all, an attacker might be able, if he can access the repository, to place big objects there and thereby downgrade, or like DOS, other entities publishing in this repository. And in the future, when RPKI grows, objects might naturally become the size, and then you could also get problems. Okay, let's come to the last slide of the vulnerabilities. So I mentioned that we saw inconsistencies in the processing, and we even saw that these inconsistencies already manifest in real-world objects. And the most severe one was an inconsistency in Fort, which is an RP implementation, which didn't accept objects which had an additional subject name, which is just an optional field in the RPKI object. And this led to over 6,000 prefixes by Amazon not validated by Fort, and therefore effectively any system using Fort would not have these Amazon prefixes protected against hijacks, which of course is a big problem. And after the disclosure, they are still working on it to get all these optional names removed to ensure that their objects are accepted by all RPs. Right, so now let's come to a conclusion. So first of all, as I showed now, inconsistencies can be a problem because they might silently downgrade RPKI protection. Because if you test this with your own RP and it works, there might still be other implementations which don't accept your objects, and therefore your resources are not protected even though you think they are. Then what we also saw by the sheer amount of vulnerabilities we found is that the availability of a fuzzing framework or some means of fuzzing is essential to ensure the quality of the software, which is also why we make our tool open source. With the tool, we detected 18 vulnerabilities and 7 inconsistencies. And maybe as a final observation, RPKI deployment is increasing fast. So we see more and more systems using RPKI, which is why it's so important that the quality of the software components keeps up to speed with the deployment. Because if you have a lot of deployment, but the software is not good enough, then you don't have a big benefit. So it's important to keep the security of the software in mind and to emphasize the resilience of the software and also to standardize different implementations to prevent inconsistencies. And that's it. Thank you for your attention. If you have any questions, then you can ask now or drop me an email. And I also want to note that we wrote a blog article on this. So if you're interested, you can check the right blog, which should publish our blog article in the next 2 days, probably. Thank you.
Thank you. Do we have any questions?
Hello. Yeah. So I have like a stupid question. So I was wondering what is the threat model in this like these sort of attacks? Like who is attacking the RPs? That's my question.
That's a good question. Thank you. So basically anybody that owns IP prefixes can attack because you are able to set up your own RPKI repository. That's like part of the infrastructure. And by setting up this repository, you can put arbitrary objects, of course, in your repository. So you can also put malicious objects there and therefore be able to crash, as I said, all RPs on the internet. And you would do this, for example, if you want to attack a certain system and want to hijack the resources, which are protected by RPKI. But if you crash the RP, then they are not protected anymore, so the hijack would go through, and therefore you could attack it. That's the idea.
Yeah. Okay, thank you.
Sure.
Hello. I have a question about the, let's say, the ratio of memory-induced errors or found by the vulnerabilities versus storage-related.
Sorry, again? Can you repeat? Sorry, I didn't understand.
I just wonder how many of the found vulnerabilities are and possible attacks ensuing from this leverage file system errors versus memory.
Okay, now I understand the question. Yeah. Okay, so the only thing on the file system we found was the path traversal, which is just one vulnerability, and the remaining vulnerabilities are all basically processing errors in the RPs. So you generate an object that has a manipulated field, for example, a field not matching the parent, or maybe a completely malformed object, and then the RP doesn't handle this properly and just crashes.
So it's memory.
Yeah, right, exactly, yeah.
Just a quick question on the size of the RPKI world. So how many nodes are deployed today and how many different implementations did you actually test? Mm-hmm. And are those maybe forks of each other? So what's the diversity in the ecosystem?
Yeah, that's a very good question. Thank you. So right now we see 4 major implementations of RPs, and we tested all of them. 2 of them are well maintained. 1 is kind of maintained, and I mean, yeah. So basically, there's one RP with a very big market share of over 80%. About the nodes deployed, I can't give you the exact number. My colleague might be able to. I think it's about 70 repositories right now. 63, right? Thank you. And about 3,000 RPs that are running currently, but we don't know if all of them. Yeah? Do you have a better? For 5,000 now? Okay, perfect. We don't know if all of them are actually used for routing decisions. Some of them might just be experimental setups. Yeah, and about who uses RPKI. So we have about 50% of systems that issue RPKI objects, and about 25% that use RPKI information for routing decisions. Yeah.
Hi, my name is Cameron Morris from the University of Connecticut. Thank you for the talk. My question is about the path traversal vulnerability. That's a pretty severe vulnerability. I would think that those are often caught by traditional static or dynamic application security testing. Did you look into, or do you have any speculation of why that wasn't caught by those?
Yeah, that's a very good question. It might be for historical reasons. So basically in RPKI you have two different options for communication with the repository. So there are two protocols basically in RPKI. And funnily enough, like one of the protocols implements the check properly and one doesn't implement it. And the probable reason for this is that initially they didn't use, in the other protocol, didn't use the location of the object as the storage location on disk. And then they changed it, so that's probably why. So basically they didn't notice that this might lead to a problem now.
Okay, thank you.
Sure.
Let's thank the speaker again.